Good. My name's Marcus du Sautoy, and if you can't hear me, I will pick up the microphone, but I do talk quite excitedly and loudly. I'm a professor of mathematics at the University of Oxford, and actually I think we do celebrate the negative very much. Probably our greatest theorem proved in the last 350 years was about the non-existence of solutions to a set of equations. So I think in some sense, if you go right back to the Pythagoreans, you can't write the square root of 2 as a fraction. We love the negative. So a few years ago, I took over a new position in Oxford as well as my professorship in mathematics, which is this thing called the Professorship for the Public Understanding of Science. Which always kind of amuses me as a title because I think most people think I must know the whole of science, and here I am to explain it to the public. And I think, you think back who at any stage in history sort of knew the whole of science, you probably have to go back to Galileo, Newton and Leibniz probably, and even they maybe not. But actually when I took over this professorship, it started me on a kind of journey to think, could there come a point where science knew it all? We seem to have so many amazing scientific discoveries being announced in the newspapers every week, and physicists sort of talk very grandly about the theory of everything, that we might get close to a moment when we have a description in equations for the way the physical universe behaves. But is that actually possible? And even if we did, would we know we had actually got a theory of everything? So it sort of started me on a journey which I've been on for the last 3 or 4 years, just wondering whether there are limits to how much science can know. And actually, as a mathematician, of course, we grow up on a theorem which says there are limits, Girdles' Incompleteness Theorem. So I thought about taking my own mindset of mathematics to the sciences to have a look and see in each of the sciences what sort of limits there might be. And it's culminated in this book, which is very timely for this meeting, called What We Cannot Know. Oh, this has gone completely. Are you okay with these? Right, that's fine. Called What We Cannot Know. So this was published last month. So this is a kind of description, and I actually divided the book up into 7 what I've called edges of knowledge. And so what I thought I would do was just as a kind of teeing up for this whole meeting, where we're going to go into many of these edges in detail, but just give you an overview of what I thought as a mathematician and a scientist were regions that I thought there might be places that we can't go that will be beyond knowledge, beyond the knowledge of sciences. I think it's always very dangerous at any point in history to do this, and I kept in mind a couple of stories of people who said we'll never know things. Kelvin, of course, famously said at the end of the 19th, beginning of 20th century, physics is finished, it's just now decimal places. But the story I kept in mind was this one by Auguste Comte, who in 1835 declared very confidently, we shall never be able to study by any method the chemical composition of stars, which at the time seemed a fair comment, because how are we ever going to visit a star, dig out some stuff, take it back to the lab and see what it's actually made out of? But of course, he hadn't taken into account that although we still haven't visited a star, stars visit us every night. And so a couple of decades later, the light was analysed, and we probably have an incredibly good description of what the chemical composition of stars is. So I kept that in mind on my journey, and I think perhaps we should as well, that how can we ever say at any point in history that there won't be something that will appear to completely change our views? And that's of course what science we love, is kind of black swan events. But that said, Girdles' Incompleteness Theorem, we have been able to look in on ourselves and prove limitations. So why couldn't we do that in some of the other sciences as well? I'd quite like to throw into this debate as well another strand which I took in this book, because the person I took over from in Oxford as a professor for the public understanding of science was Richard Dawkins. And Richard Dawkins obviously spent a lot of time towards the end of the tenure of his professorship talking not just about science but also about God. And his book, The God Delusion, put him in the firing line for a lot of debate about God. And so I got a lot of questions when I took over this job about my beliefs in God, which I tried to kind of bat away. But I remember having one discussion on BBC Northern Ireland radio on a Sunday morning, which, you know, religion is never far from people's minds on a Sunday morning in Northern Ireland. And actually, when I asked this journalist, well, as a mathematician, I like a very clear definition. If I'm going to prove something exists or it doesn't exist, you need a very clear definition of what it is you're trying to prove doesn't exist. We're very good at proving things don't exist. So the journalist, interestingly, said, well, yeah, God is something which transcends human understanding, which is undefinable. And, you know, at the time I thought, well, that's a cop-out. You've just wiped us all out of the conversation, because how can you intellectually engage with that? But then I thought that was actually, afterwards, maybe quite an interesting definition to work with. And so I've sort of taken that also on my journey in this book as a kind of exploration. Okay, if we can, as scientists, define what is something will transcend our understanding, how does that fit into questions about religion as well? And I talked to a philosopher friend of mine in Oxford. He's a Wittgensteinian, Stephen Mulhall. And when I was talking to him about this idea, I was doing a debate with the chief rabbi in London, and he referred me to this Marxist theologian in Oxford, which I thought was quite cool. I'd love to be a Marxist theologian. That sounds such a cool title. Called Herbert McCabe, and he's got a lot of very obscure texts on Christian liturgy, but he had one essay which had some interesting things to say about sort of more fundamental questions. And he makes this statement: to assert the existence of God is to claim that there is an unanswered question about the universe. So he was also sort of pushing this idea of God is actually, for him, was a very abstract idea, and that religion very often committed iconoclasm by actually giving this very abstract idea properties it never should have had. And that's what we get served up as kids, this kind of bastardized version which we quickly reject. But maybe we're throwing too much out, and maybe it's worth coming back to the idea of transcendence being something, having properties that are worth exploring, even if you can't know it. So I thought that might be worth also us keeping in mind as another strand, if you're interested. I certainly was kind of intrigued, having been forced to engage with this debate a little bit more than I thought I would have to. So I'm going to give you a little just guided tour of some of these edges of knowledge, which we're all going to talk about in greater detail, and you're somehow, many of you, of course, much more expert than I am. It was kind of a journey of discovery for me a little bit, going outside of my comfort zone of mathematics. But I think that's what this meeting is partly about, is going outside of our own comfort zones to meet people in other disciplines. So my first edge that I looked at is actually quite related to my own subject of mathematics. Mathematics I talk about as the study of trying to understand patterns in the past, such you can predict perhaps into the future. And so the first edge was really about trying to understand how much can we know about the future. Can we know the future before it becomes the present? Or are there unknowabilities about the future? And actually I took with me on my journey to these edges of knowledge an object which kind of helped me on my journey. So I think the ultimate symbol of kind of unknowability is a dice. The whole point about why dice are exciting and we play in games with them and gamble with them is because we just don't know what this is going to do next. If I throw this on the floor, I get a 1, but I'm intrigued to keep looking because I don't know what's going to happen next. So the casino dice is my kind of object that I took about asking the question, can I know the future? Can I know how this is going to land? I mean, my hero, I guess, on my journey to want to know the future, I sort of chose mathematics as a subject because I wanted security. I was a spotty teenager, very insecure, and I loved the idea that mathematics gave me some secure knowledge to hold on to. And I guess Isaac Newton is probably my hero in the thought that we could know the future before it happens. His laws of motion really say, well, if I know how this thing is set up, and I know the laws of motion, and I drop it, surely I can just run the equations to it's landed 1 again. Surely I could have worked that out from the equations of motion and Newton's laws. So, Newton did give us this hope, and Laplace, of course, talks about it. If we know the complete setup of the universe now, we will know what is going to happen into the future, and everything is determined. But if Newton is my hero, I suppose Poincaré is the nemesis in this story, because Poincaré said, well, yeah, sure, if you know the complete setup of the universe, you could run the equations, but unfortunately, even a very small error could cause a completely different outcome to result from your equations. And this is his discovery of chaos theory, that just a very small inaccuracy can cause your predictions to go very wildly different within a few days or a few years. And I suppose there's some lovely examples of just how chaos, this inability to predict, arrives in just very simple systems. It doesn't have to be a complicated system. My favorite of these is this little desktop toy I have, which I use to make all my decisions. So you'll see it's on the side. There's a little magnets, and there's little answers to questions. So there's yes, maybe, definitely, no way, try again, ask a friend. And so I haven't got a clue when I set this. So is it England going to win tonight against Russia? So we set the thing off, and I've got a little video of an experiment that was done. So this is 3 magnets and the pendulum being drawn to the magnets. And you can see it's just almost impossible to predict as this thing flies off which magnet it's going to end up at. And actually, Poincaré discovered chaos by trying to understand the solar system. So it ended at the bottom one here. So the solar system, this is a little bit like a solar system. 3 planets and an asteroid flying around the planets attracted by the magnet. Poincaré realized that even with 3 planets, you cannot, a very small shift in the location of one of the planets will cause the asteroid to land somewhere different. So apparently England are definitely going to beat Russia tonight, according to my, so we'll see how good that prediction is. Here are a couple of models that I did to show the sensitivity of this particular little dynamic system. I started the pendulum off in the top left-hand corner, and I just changed one of the decimal places, 6th decimal place, very slightly in each case. And you can see that in the first experiment it ended up at the blue magnet, the second one the red magnet, the third one at the yellow magnet. So very different outcomes with very little change in the initial conditions. And this is the challenge, I think, of trying to predict the future, even if the universe is deterministic, and we will come back to that question a little later. The trouble is that there are regions which are very predictable. That's why maths has been successful. That's why we've landed a little spaceship the size of a washing machine on the side of a comet. But there are also regions which are unpredictable. So if you start near a yellow magnet, you're going to end up at the yellow magnet. There are also other regions which are quite predictable. If you start sort of opposite the yellow magnet, then it swings back and forward, and the red and blue can't attract it. So it's interesting that there are regions which you can know, but there are other regions where suddenly that ability to know is lost. So I started the pendulum off in the top left-hand corner. And this is an area which is fractal in nature. It has infinite complexity. As I zoom in on it, I never get just a region of a single color. And so this means that just a very small change will take me over. So I should have explained the picture here. If you start the pendulum over a red region, that says the pendulum is going to end up, when you release it at that point, at the red magnet. So if I start in the yellow region, that big yellow blob, I end up at the yellow magnet. But at the top left-hand corner, it's just very unclear. A very small change can take me from yellow to red to blue, and so that small change can result in a very different outcome. So chaos theory says that, I think it does express some sort of limits to knowledge, because we can never have complete knowledge of how the universe is set up. And that very small change at some decimal place might cause you to have absolutely no control over what's going to happen. With the weather, it's 5 days. With the solar system, it's a little longer, fortunately, but it's still, we've been able to show that the solar system is genuinely chaotic, and there are small shifts in the orbit of Mercury which could cause the solar system to completely fly apart. But that's fortunately not 5 days, that's 5 billion years or something. It will be already swallowed by a sun by then. I think a mention of political implications of this was raised a little earlier, and I think there are political implications. And as well as an object, I also took a person with me, because I'm not an expert in all of these areas. And the person I took on my journey to the edges of kind of trying to predict the future was Bob May, Lord May. He's a cross-party member of the House of Lords now. Bob May discovered chaos theory in a lot of biological systems, in particular population dynamics. So if you have populations can be very stable and, or periodic, but sometimes if for example, lemmings who are very productive, their dynamics are very chaotic in nature. It's very hard to predict from one season to the next how many lemmings you're going to get. But he's now looking at the banking crisis that happened in 2008 and trying to understand the economy is controlled by equations, it's numbers. How can you be sure that something very unexpected isn't going to happen again? The reason a lot of people make money in the economy is because the mathematics is very predictable. You're in nice solid yellow region and people just make money off it. But when can you know that it shifts to another region and you're out of control? And he said, I went to had lunch with him in the House of Lords, and he said to me, not only in research, but in the everyday world of politics and economics, we'd be better off if more people realize that simple systems do not necessarily possess simple dynamic properties. So I think it is not just interesting for a purely philosophical debate, it's very important that society as well understand when we can know and predict and when we can't know. And also not to use it to say, well, the weather's chaotic, therefore climate change doesn't exist. That's just silly. Those are predictable things. We can know the tides happen even though we don't know when the waves are going to crash. The climate change is a similar sort of thing. I was interested to go back to my dice, actually, and understand whether it was chaotic. And I got a little bit of a surprise, actually. This turns out to be more predictable than I thought it was going to be. So I discovered a piece of research by 4 Polish mathematicians who've done some, by some Polish mathematicians. I'm not going to even attempt to say their names. I read the audiobook for this, and when I hit these 4 Polish names, I gave up and said to the Polish team, I'm afraid to say. So, and they'd done some analysis with cameras to watch the dice as it fell. And they discovered that actually, so I could do the same thing. I colored the magnets and drew that picture, which helped me to predict the behavior of the pendulum. So they did similar things. They colored the 6 faces of the dice and drew sort of pictures of the setup of the dice to be able to predict which side it will land on. And it turns out this is more predictable in some circumstances than you might expect. So this is actually quite a soft floor here. So if there's a lot of energy dissipation when the dice hits the floor, then actually this is much more predictable. So here are their pictures to show whether you can know the dice or not. And the top left-hand corner is the behavior of the dice when a lot of energy is dissipated. And you'll see it doesn't have this fractal quality. It's large bands of color, and so a small change isn't going to cause the dice to actually change sides very quickly. There's obviously threshold moments where actually moving across from the yellow to the blue will change the side the dice happens. So if you take anything away from this, my presentation or my book, it's this. If you play in the craps table and they seem to have a rather soft table, more often than not, the dice actually lands on the number that was on the bottom of the hand here. So I'm going to put the 1 here and let's see. No, it was a 6. There you go. I was completely wrong. That's the trouble with physics. That's why I became a mathematician, because I like security and know when that's going to happen. Anyway, so maybe the point is that this is actually a bit harder than I thought, and we're drifting into more fractal regions. That's my way of getting out of this. So actually, if you're throwing it, say, on an ice rink or something, and it's bouncing, there's not much friction even, then you have a very fractal picture, and a very small shift can take it into a completely different side of the dice. So I think one important thing is that we should know when we can know, but also it's as important maybe to know when we cannot know in these kind of dynamical systems. So that's my first edge, which of course is actually an edge talking very much under the idea of pre-20th century physics, where everything is deterministic and you run the equations. Laplace says, you know, Laplace's demon can know it all. But actually now quantum physics says that maybe even Laplace's demon will not be able to know everything. So my second edge sort of pushed me more in towards the aspect of quantum physics, which will be one of the big unknowables that will come up, I'm sure, during the weekend. So the object I took on my journey to the edge, to this edge, was a pot of uranium that I bought on the internet. It's extraordinary what you can buy on the internet these days. And it's interesting, this pot of uranium has on the side a number for each particular piece, which tells you the radioactivity. So this pot is emitting 984 bits of radiation per minute. I'm assured that it's safe to have this. I'm just told not to eat it, apparently. But interestingly, although it's telling me quite a lot, it's telling me per minute how many bits of radiation are being kicked off this, what it cannot tell me, and what we don't have any mechanism to tell us, is when it's going to do that. We do not know when a precise moment and why it's suddenly deciding at that point to kick off a bit of radiation. All we know is, on average, 984 bits of radiation will be kicked off this per minute. So we have the same mathematics that controls the dice, but my feeling is still the dice is controlled by things I could know if I knew enough detail about this dice and the equations. But quantum physics currently says that we cannot know when that's going to happen. So is this a genuine unknowable? Well, this is at the heart of Heisenberg's uncertainty principle, which says there's a trade-off for knowledge here. This isn't a wishy-washy statement. It's a mathematical equation which comes out of the mathematics of quantum physics, which says the more that you know about, for example, the position of a particle inside that uranium, the less you know about how it's moving, its momentum. And if you hope to have pinned down the, say, a proton where it is, and if you then try and measure its momentum and try and pin that down, you will lose information about the position in order to make this equation true. And you know, the double slit experiment is a famous example of the sort of unknowability of where an electron is. But I think already the single slit experiment explains Heisenberg's uncertainty principle and the fact that you lose knowledge once you gain knowledge about something else. So this single slit experiment, if you send a particle over a large distance to a single slit and then try and pick it up on the screen behind, well, if it passes through that slit and you've got the particle gun a long way away, then you know as it's passing through it must have zero momentum in a vertical direction. But as it passes through that slit, you gain knowledge about its position as well. And that has to be traded off in a lack of knowledge about the momentum suddenly. You thought the momentum was zero, you think you know the position precisely, you can't know both precisely, and it turns out that the momentum then has an indeterminacy about it and can be in a certain range. And so the more you narrow that slit, the larger the spread of the particles as they come through and hit the screen. So we've done experiments, there's experiments here with actually quite large particles going through. So in the top one, the slit is quite wide, so you've not got such clear information about the position of the particle as it goes through, which means actually you haven't lost too much information about the momentum. So the momentum doesn't spread the particle across the screen, and so you have quite a narrow band of the sort of normal distribution. But as you narrow the slit, the experiment absolutely indicates that the momentum, the information is being lost, and the indeterminacy is increasing, and such that the spread of where that momentum might fly the particle is increasing. So here's these three sort of illustrate the more you know about position, the less you're knowing about the momentum, which you thought was zero, but now has a spread either side of zero. Actually, in some ways, and we'll come back to, you mentioned Wittgenstein, a lot of the challenges here are have we got the language right? Actually, maybe this is not a problem about, oh, you can't know the position now, you can't know momentum. Maybe it doesn't actually make sense to talk about the thing having a position and a momentum. That's our Newtonian kind of mindset, that we think that things have position and momentum. And so one interpretation of this is you shouldn't think of the particle having a position until it's observed. you must consider it as being distributed by a quantum wave function which tells you the probability about where you're going to find that particle when you observe it. So you shouldn't think of it having a position. Only once it's observed does that wave function collapse. So I think that's an interesting thing to throw in. How much of this are limitations of the just language that we're using, that we're using the wrong language, which is leading us astray into thinking in different ways. So our interpretation now is that a thing doesn't have position until it's observed. But then that's crazy. What on earth is observation? You know, aren't we all part of some universal quantum wave function describing the universe? So aren't we part of that wave function? So, you know, I think there's real challenges still about what on earth we mean by observation. I'm one who believes that we haven't got a complete theory yet, and that it's the mathematician in me that believes that this can't be true, that there isn't some mechanism which will tell me when this thing is going to radiate. Maybe we don't know it yet. But you know, surely there's something like the equations for the dice, some little mechanism inside this thing which is saying when it's going to be kicked off or not. Now, I'm not the only one to believe that. Einstein, of course, also believed that quantum physics wasn't the final answer. He wrote, "Quantum mechanics is very impressive." And it certainly is. It's probably the best tested theory we have in physics. But an inner voice tells me it's not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am, at all events, convinced that he does not play dice. Now, we know, of course, and we're going to probably talk about the ideas of entanglement and the implications of that, Einstein, Rosen, Podolsky thought experiments, Bell's theorem, all of these things, I hope, will come up, actually imply that if there is a mechanism, it's a very strange mechanism. Because this mechanism is not localized at the center of this uranium, as I would have expected, some little thing that we can't quite see yet. And if we look inside, we'll find this little clock which says, emit one now, emit one now. We know that it's actually a mechanism which is spread across the whole universe and can potentially affect things at great distances. But I think, as Bell said when he proved Bell's theorem, which says you can't, Bell's theorem basically says in quantum physics you can't assign values to things before they're observed. You can really genuinely show that the things can't be set up in an entanglement experiment such that actually the particles know what they're going to do because you don't know how they're going to be observed. And he said, you know, this shouldn't be saying that there isn't a mechanism. It's just saying that we've got to be much more imaginative in what a mechanism would be if we're going to be able to understand it. Now, I took on my journey coming back to this idea of kind of religious aspect to this story about transcendence. I was quite interested to talk to a few scientists who were also religious. I think scientists divide into two camps if they're religious. They're the deists and the theists. The deists say, I haven't a clue where all of this stuff came from, and I'm going to call that Creator God. But once it's all got going, then I'm going to become a scientist and I can analyze the whole thing and God doesn't act in this world. The theists say, oh yeah, but my God actually acts in this world as well. So I was interested to talk to a theist scientist to understand, well, how is your science helping this God act in the world? So this is John Polkinghorne, who many of you may know about. He's a quantum physicist trained with the best. With Feynman, Dirac, you can't ask for better teachers than that. He was also involved in the discovery and study of quarks. Halfway through his career, he became ordained as a priest in the Church of England. As he describes himself, he says, I'm a bit of a vegetarian butcher. And so I was sort of intrigued to ask him, well, okay, how does your God act in the world? You know the mechanisms. And I wondered whether quantum physics might be his little window, because if there really is no mechanism, maybe that's somewhere that an external intelligence could say, okay, well, I'm going to put it here rather than here, and you're never going to know what it was going to do. And actually, that small change could cause a big difference in the outcome because of chaos theory. But he rejected that and said, no, that requires an observer. An observer, why should God have to wait for an observer? So he didn't think it was that. He actually talks about chaos theory as being his little window for his God to act in the world. Because humans can never know the precise setup of anything, there's always decimal places which can be played with in a way which won't change kind of energy considerations. And he believes that that's the place that God can tinker. Leibniz actually, Newton and Leibniz had this same debate actually, and Leibniz was very angry with Newton, saying, well, that's ridiculous. Why wouldn't have God set up the universe to be perfect in the first place? Why does he need to start intervening and tinkering with the decimal places? Which is, God presumably is outside of time and could do that. So it's kind of an interesting discussion. But actually, one of the big, I think for many scientists, one of the big unknowns is, why is there something rather than nothing? And that is the kind of deists will say, I don't know what the answer to that is, and that is what I call my God. And I'm not going to sort of question, I just don't know what that is. But I think that actually this edge is getting us closer to an answer to why there is something rather than nothing. I mean, my pot of uranium, where did that come from? Well, it might have, I bought it on the internet, but where did it come from before there? A mine, but where did it come from before there? Or a supernova? Well, where did all of the stuff come from? And actually, Heisenberg's uncertainty principle has many versions about measurement. Position and momentum are related, but also energy and time are related. And so if you look at a smaller window of time, the energy content might have been 0, but you can get these fluctuations such you can get a little bit of energy appearing out of what you thought was a 0 energy region. And that energy E equals mc squared gives you the idea of mass. So you can have these fluctuations where you thought there was 0 energy, but then things can appear. And of course, that's Hawking's idea of Hawking radiation at the edge of the event horizon of a black hole is exploiting this, that these fluctuations can cause particles and antiparticles to appear, such it gives a mechanism for black holes to radiate. So maybe, and you might say, well, I need still empty space in order to be able to play a vacuum thing, but quantum gravity might be also being able to get us even empty space out of nothing. So it's interesting that even the great unknowable of why is there something rather than nothing might be something that is within reach of the sort of physics we're sort of producing. Right, well, I've given you 2 edges. I've got about 10 minutes to race you through what I think are some of the other edges of knowledge. So actually, I was very intrigued by the idea of what my dice and my piece of uranium is actually made out of. So if we dig inside, the ancient Greeks thought that things were made out of earth, wind, fire, and water, and they were continuous structures that you could just keep on infinitely dividing. But then we had this shift from infinitely sort of divisibility to the idea that things were made out of indivisible things, atoms. But then we discovered the atom of uranium isn't so indivisible. We can dig inside that and find, no, it's got smaller bits. It's got an electron, proton, and neutron. And then we thought that was it. What a beautiful description. 3 things which can make the whole of the periodic table. It seemed so beautiful and so right and so wrong, and it turned out, because then we discovered all of these fundamental particles in the cosmic ray interactions, and we suddenly had physics turn from being a beautiful mathematical thing into a horrible, messy biological thing with loads of particles which didn't seem to make any sense at all, until we saw the mathematics inside this and made sense of how to put these fundamental particles together into beautiful sort of pictures, which implied that there was a kind of missing layer. So these are some of the fundamental particles, which gave us the realization that considerations of symmetry said that actually there are 3 quarks at the center of these protons and neutrons, which make up the proton and neutron. The proton and neutron come apart. And so now we have our current state of particle physics is that here we think that this is the bottom layer. Electron and these 6 quarks, well, 12 quarks now, and this is our belief, and the mathematics is kind of saying there's an indivisibility about this. They're point particles, so they don't seem to occupy any space. But is this the last layer? So that's my other question about, can we ever know? And history tells us each time we think we've hit the bottom layer, we get a surprise. And of course, we have a string theorist here who's going to talk a little bit about, well, maybe the bottom layer is these vibrating strings, which will tell us what makes up matter. So I think going infinitely, trying to dig infinitely deep inside my dice or uranium, that's an interesting unknowable. Whether we could ever know that we've hit the description of what makes up particles, Could we ever know that? I think looking outwards, so that was the very small. What about the very big? What about our universe? How big is our universe? Is the universe infinite? Well, of course, we thought we were at the center of it all, and each generation we sort of pull out and realize actually we're more and more insignificant as we go on, so we're just a planet around a sun, but then we realized that solar system was just part of a much larger thing. We're really on the outskirts of our galaxy. Then we turned out we weren't just a single galaxy. There are loads of galaxies. But there is actually a limit, of course, to what we can actually know about our universe, because information travels at the speed of light. The Big Bang went off 13.8 billion years ago. It means that information has only had a finite amount of time to travel to us. So we have a bubble around us, a bit like going back to the ancient Greek model, a bubble of information beyond which our cosmic horizon, beyond which we cannot receive any information. We can wait for that information to come in, but it will always be finite. So if the universe is infinite, could we ever know that it's infinite? Is that an unknowable? It's actually even worse than this, because you might say, well, we can wait for this bubble to grow and we'll start to see more and more. But because of the accelerating expansion of the universe, actually things are being pushed faster outside of that cosmic horizon than the cosmic horizon is growing. So we're losing information. We will reach a point when we won't see any other galaxies. We will think, if we'd been born, evolved as a species at this point, we would think we were back to the ancient Greek idea of something in a void. We would just be a single galaxy and we wouldn't know. There'd be no way to know about those other galaxies, which is extraordinary. So, you know, the limits of our knowledge about the cosmos might be limited by this cosmic horizon, this bubble. We are basically living in a Truman Show, if you know your Jim Carrey movies. Although actually, of course, now that was my what I grew up on, but I've had to align my position in the universe that maybe we're not the only universe, that maybe we're part of a multiverse. This is our best explanation for why the constants of nature are set as they are. That actually it's a kind of evolutionary model where there are other lots of universes with different constants of nature where life doesn't get going. So could we ever know about these other multiverses? I think possibly we could. There's no reason they wouldn't perhaps have some interaction with us to be able to know. So that's 4 out of 3. Well, I've got 5 minutes left for the last 3. I will scoot through these. I think the nature of time is also a big challenge for knowability. And there are lots of challenges in trying to understand time. Here's St. Augustine, who said, "What then is time? If no one asks me, I know. If I wish to explain it to one that asketh, I know not." And I think that trying to pin down time is one of the big challenges of physics at the moment, whether it's an emergent phenomenon, maybe time isn't as basic as we think it is. Time, we think, started at the Big Bang, that you can't talk about before the Big Bang, that's like saying what's north of the North Pole. But that kind of idea of physics is changing a little bit, and so there are thoughts that, well, the Big Bang is under current model of physics where quantum physics and general relativity don't fit together. So maybe there's a way to extend time before the Big Bang. Does that make sense? What's going to happen to time? It's a pretty bleak future we've got ahead of us thanks to this accelerating, expanding universe. If dark energy is really just pushing things according, the more space we have, the more dark energy there is, we're going to end up with a very boring universe, which is just cold, nothing going on. In fact, time itself will run out because we'll just be left with photons and gravitons. There will be no more time. Which is pretty bleak. My colleague in Oxford, who I took on my journey to the edge of time, Roger Penrose, has seen an opportunity in this, though, and he now has this idea of the cycles of time, that if you lose a sense of time, you also lose a sense of distance, and that gives you ability to rescale the universe. And so that actually what might be a very large, spread out universe full of photons of light can be rescaled to a point of infinite density full of light, which is another Big Bang. So he has this idea that there are cycles of time, which again raises the question, well, before we had time beginning and ending, but now is it time infinite in the backwards, and is it infinite forwards? Could we ever know that? So that's the nature of time, I think, is a fascinating one. The nature of, I mean, I've dealt with a lot of mathematical and physical things, but I think the nature of consciousness, the hard problem of consciousness, which we're going to come to tomorrow, is also, by its nature, one that philosophers say you cannot know. this is a problem by its nature. We're stuck inside a system, which I think is a theme that's going to come up. The idea that if you're stuck inside a system, how can you analyze yourself? So Wittgenstein as well said, isn't the hard problem of consciousness rather similar to a box that we all have, and inside it is a beetle, something we call a beetle, but I can never look inside your box, so your beetle might be completely different to my beetle. Is this, again, just a question of language? Well, I was going to, let me skip through these, because I think that, is it okay? Yeah, I don't want to, because, okay, if I'm trying to, you see, I think that actually we're in a golden age with we're a bit like Galileo with his telescope looking into the outer space, that suddenly he was able to see things we'd never seen before. Neuroscience is in a similar stage where actually we got things can look inside that little box of Wittgenstein's. An fMRI scanner is starting to tell us a little bit more about what's happening inside your heads. But if I'm trying to understand something like consciousness, as a mathematician, one of the tricks I often use is, rather than trying to understand the thing I'm looking at, much better to look at all the things which aren't it. And if I can understand that, very often that gives me very clear knowledge about the thing that I, almost look at the thing away from the thing you're looking at. So in the hard problem of consciousness, I think for me, one of the most revealing things is looking at when something isn't conscious and trying to understand what the difference is. Why is that thing we regard as not conscious? So animals, I think, are a very interesting example. So, which animals, I mean, I don't know how many of you have pets, but whether you believe your pets have the same sort of level of consciousness as you. And how can you ask an animal whether it has a sense of itself, what it feels like to be that animal? Well, Gordon Gallup came up, animal behaviorist, with an interesting, it's a rough way of testing whether an animal has a sense of self. But what do they believe when they look in the mirror? What do they think that is? Do they believe that's themselves? Or are they just sort of showing off their dancing moves there? But Gordon Gallup came up with this idea. If you mark an animal surreptitiously with a mark on their forehead so they can only see it in the mirror, what's their reaction when they look at their image in the mirror? Many animals won't react at all because they're not interested in the other animal. They might touch the other animal. But this is an orangutan. And the orangutan, when he looks in the mirror, has a reaction. And a reaction that we would have as humans is saying, what's that weird yellow mark that's on my forehead? And the reaction of putting their hand up to their forehead rather than to the image in the mirror is an indication that they recognize that that's an image of itself. This orangutan seems to be really pissed off, actually, that he's been had this yellow mark put on him. So it's interesting. What animals have a similar response? Well, it's very few, actually, species. Chimpanzees and orangutans seem to be the only species which have a universal reaction to this. Dolphins as well, there is some evidence. Obviously, it's harder for a dolphin to go like this underwater, but there are ways to test that. Humans as well, of course, but very few other species. Now you might say, well, dogs, I have a dog and I'm pretty sure that dog is conscious and my dog uses sense of smell. So yeah, this is a very rough and ready, but it's interesting to just mark different transitions in brain activity. And I think actually the question of when humans become conscious, because here are some pictures of me as I grew up. Now, as a baby, I don't think I would have passed the mirror self-recognition test. I didn't have a sense of self. My sense of self evolved and developed over the time I grew up. But at what point did it shift so that I would pass that mirror self-recognition test? Turns out if you put a baby that's about 16 months old in front of a mirror and you mark them very surreptitiously, they have no reaction to that mark. And they might even go and try and touch the person behind. But there's an amazing moment, a transition. Something happens in the brain about 20 months where you put a 20-month-old and put a mark there. They immediately go, what's that? Really strange. So for me, that's interesting. What has happened in the brain that has changed the nature of your sense of self at that point? And I think this difference of what makes somebody conscious or unconscious. Here's a very interesting. I think this is slightly unrelated, maybe, but you have patients. This is very important, I think, again, politically, for example, because if you have patients in a hospital that you consider as just in a vegetative state, but actually they're not in a vegetative state. They are, in fact, conscious inside there, but locked in and unable to move their bodies. It's really important to know that. So the idea of knowing when somebody is conscious is really important for considerations of what you're going to do with that patient. And now we're beginning to develop a sort of conscious ometer, which is you can stick somebody in an fMRI scanner and you can ask them to imagine playing tennis. Now that isn't an automatic response. If I do that, there's a lot of automatic kind of reflex responses that vegetative state patients have. But the act of imagining you're playing tennis is not one that's believed to be a sort of a response to just physical stimuli. It's almost a mark of your free will that you're deciding now, okay, I'm going to imagine playing tennis. You can pick that up in an fMRI scanner because the motor neural activity, even though they're unable to move their body, you can detect that they're thinking about moving their body. And you can actually even have a conversation with these people now because if you imagine a journey through your house, it activates a different bit of your brain. So if you want a yes or no answer, you can say, well, imagine playing tennis if the answer is yes. Imagine going through your house if the answer is no. So extraordinary that we are starting to get inside that box of Wittgenstein's. This, for me, was the most exciting, which was going to Giulio Tononi's lab in Madison, because another time we all lose consciousness is every night when we go to sleep. So what's happening in the difference in the brain activity when you're in deep stage 4 sleep and have no conscious experience at all? Well, in the past, how could you ever ask anybody or investigate that brain? But now we can. We have this thing, transcranial magnetic stimulation, where you can basically switch on some neurons and say, okay, what's the logical implications of turning on this set of neurons? You know, the brain is basically a logic gate. It's got, if this one's active, the synapse sparks this one. This is the awake brain. Let me play that one. Oh, it's still going, you see. This is the interesting thing. So the stimulation was at this point here. We just switch, turn those neurons on. The effect is this kind of cascade across the brain, a sort of feedback across and then a feedback. These kind of, the idea of the strange loop in some ways. Douglas Hofstadter's book, Girdles was all about trying to understand the idea of consciousness as maybe feedback systems. And we see during this, an awake brain, this feedback mechanism happening, occurring across the brain, feeding back to the point of activity. This is the same patient when they're asleep. So you do the same transcranial magnetic stimulation, you fire those neurons, everything is now localized behavior. There's no cascade across, the network is completely different in behavior. It's as if the network has gone down, the tide has come up and there isn't this kind of feedback behavior. Giulio Tononi has kind of tried to capture the nature of this network and the difference in behavior of the network in the awake brain and trying to see the sort of logic behavior of the brain when it's awake and you turn on these neurons as opposed to when it's asleep. And he's now got this thing called a coefficient of consciousness. So a mathematical formula which captures what it means to be me, which of course I love. You know, what the idea, suddenly just consciousness has become a piece of mathematics. Who wouldn't want that? And so this actually sort of tries to capture networks which have different degrees of sort of integrated behavior and feedback behavior, which he believes is what you're seeing in these conscious awake brains. And it means, of course, we can apply this to different, not just the network of the brain. I think one of the big challenges for the hard problem of consciousness is, that iPhone you have just held up, is that ever going to be conscious? Or maybe it's not an iPhone. It's probably something Swiss or something, Swedish. Or, can we ever know that that network is conscious? So it might pass all the tests, but we still won't know whether it really feels. We assume, I think this is important about knowledge, is that we assume a lot about homogeneity in the universe. I assume that you're very like me, so I assume that you're having a very similar experience to me and that you're not all a bunch of zombies. Just send down your avatar this morning to see the... But Giulio Tononi's coefficient of consciousness, I think, gets us some way towards the hard problem of consciousness. Interestingly, he's set up two networks. This is a real challenge to the Turing test and the idea of trying to distinguish between zombies and truly conscious beings, because these two networks have the same input-output behavior. If I activate certain neurons in this network, they have the same output. So if you interacted with them, you would believe they were exactly the same beings. But he believes that the one on the left has a very high coefficient of consciousness because the way the network works is a lot of integrated behavior, feedback loops. The other one is just a push forward. And it has, he believes, this has 0 level of consciousness and just, but has the same input-output behavior. And you could apply this to the human brain. You could set up a human brain and just, it's a completely formalistic thing to turn one of these networks into just a push-forward network, which would have no 0 coefficient of consciousness. So this would be an example of a zombie. Well, that was the last one, the penultimate one, and I think I will, because we're just about to embark on the idea of Girdles' incompleteness theorem, I will just say that that was my last edge, which of course is in a way the one that was closest to my own. Hilbert raised this challenge that you thought we could know it all. For the mathematician, there is no ignorabimus, and in my opinion, not at all for natural sciences either. The true reason why no one has succeeded in finding an unsolvable problem is, in my opinion, there is no unsolvable problem. In contrast to the foolish ignorabimus, our credo avers, we must know, we shall know. Was he true? Well, of course, Girdle, just shortly after he gave this speech, Girdle came up with his incompleteness theorem, which says that within any system for mathematics, there will always be true statements within that cannot be proved within that system. And I think that's important to be very clear of. You're saying that within that system it can't be proved. We can know it's true by working outside the system. But that system itself has its own unprovable truths in it. But this idea of being stuck inside a system, I think, is one which will come up a lot in the unknowable. And of course, Girdle exploited this idea of these linguistic statements which we can't make sense of. This statement is false, doesn't have a truth value. But statements in mathematics either are true or false. And this was Girdle's great breakthrough, was to realize you can make this statement is unprovable into a statement using Girdle's coding just about mathematics, which either has to be true or false. And the only way this can work is if it's true and unprovable. But I'm sure we're going to go more into that in our next session. So there's my kind of overview of sort of certainly lots of things I can't know. But there are, of course, lots of things beyond this as well. But this is kind of my exploration through potentially what might be beyond us all.
Thank you so much.
Thank you.
Thank you so much.